Yes, we can see.
Hello? Yes?
Yeah.
Okay, good. I think maybe this, let's hope it's working now. Okay,
Yeah.
so this presentation is about X-Pulse, broadband NMR that you can put on your benchtop. So we'll first look at a brief history of benchtop NMR and where it's come from and where we are today. Some people may recognize this. You have to be quite old to recognize this, but this is what NMR instruments used to look like when they first came onto the market in about the 1970s. This is an old Varian instrument from about 1970. These were continuous wave electronics, not Fourier transform in the way all modern instruments are. They had a large permanent magnet here underneath the bench, operating at 1.5 Teslas or 60 megahertz operating frequency. And they used a paper chart recorder to record the spectra. So these were very basic and very simple instruments, but they did a lot of good work back in the 1970s and later. Then along came superconducting magnets, like this one here. And I'm sure all of you listening now will have seen one of these kind of instruments in your university chemistry laboratories. So these are superconducting magnets with very high field strength and very high operating frequency, typically 400, 500, 600 megahertz, providing very high performance for research chemical activities. But the problem with these kind of magnets is that they need liquid helium, they need liquid nitrogen, they need compressed air, and they need special facilities. Most of the time you see these in a special NMR laboratory where they have trained technicians to look after them. So they're good machines, high performance, but expensive and difficult to look after. So that brings us up to date to look at where we are now. And this is where we are now. In some sense, we've gone backwards because we're now going back to permanent magnets, similar in performance to the magnets in the old Varian system, but with completely modern electronics and up-to-date functions. So this is our X-Pulse instrument. It's a 60 megahertz magnet in this box here. Has a very high resolution of a 0.35 hertz line width. It has good signal to noise. It's a broadband instrument, which means it can look at many different NMR nuclei. We can do flow measurements with it. We can do variable temperature measurements, and we can do many of the advanced experiments that until now you could only do on high field superconducting instruments. So we're going to talk a little bit about many of these things as we go through this presentation. The most basic performance is a one-dimensional proton spectrum. And this is an example of the one-dimensional proton spectrum that you can get from our X-Pulse. It's very high resolution, very high quality, and almost as good as you get from a very high field instrument. The X-Pulse also has very high sensitivity, as you can see in this example here, which is a 30 millimolar sample of a compound called quinidine. And this was measured in just 20 minutes with a very clean baseline, as you can see here, very little noise. So this is an illustration of the quality of spectra and sensitivity that you can get. Having high resolution and good sensitivity means that the peak integrals that are generated through the software are very accurate. In here we can see that we have integrals of 3, 3, 2, 1, and 1 from these various different groups in this spectrum. The protons at positions 5 and 8, so that's this one here and this one here, are calculated at an integral of 3 because they each have 3 protons on the groups. Position 4 here has an integral of 2 because there are 2 protons attached, and groups 6 and 7, these two here, both have integrals of 1 because there is 1 proton in total attached to them. Of course, there are many more peaks shown here because of the splitting of the proton resonance caused by nearby protons. But the integrals are shown to be very accurate and very helpful in interpreting the spectrum. This is an example of more advanced experiments that you can do with the X-Pulse. These are carbon-13 measurements on a compound called trans-ethyl crotonate. And this is a pulse sequence called DEPT, which is designed specifically for carbon measurements. And it has a number of different alternative parameters. So the normal one-dimensional carbon spectrum is shown here. And these 3 different variations of the DEPT sequence allow different carbon proton groups to be highlighted. So the DEPT 45 shows CH, CH2, and CH3 groups. DEPT 90 shows only CH groups. And the DEPT 135 shows a CH, CH3 as positive peaks, that's above the line, and CH2 groups as negative. So by using a set of experiments like this with the different parameters, you can help to identify the carbon proton groups in the spectrum. These are examples of even more advanced experiments, which are commonplace on the high field instruments, but until now unusual for smaller benchtop instruments. At the top right here is the standard proton spectrum for this compound. In the left-hand side here is what's called an inverse experiment, or a 2-dimensional experiment called HSQC. And the purpose of this one is to show a proton experiment or proton spectrum in one dimension and a carbon spectrum in the other dimension, and show where the couplings exist between the protons and the carbons, so that you can help to identify further the structure of this molecule. This experiment, HSQC, helps to identify carbons and the protons that they are directly coupled to. And it also shows us in the different colors what's called a multiplicity of the groupings. So we can see from the different colors whether these connections are with CH or CH2 or CH3 groups. Finally, this bottom right picture here is a different kind of 2D experiment called a HMBC, which gives information about the longer range couplings along the length of the molecule. So by looking at all of these three experiments together, you can get some very valuable and important information to help you analyze the structure of the molecule. Let's come back now to something a little bit simpler. Let me show you an example of how NMR measurements can be used for an industrial application. These are three spectra taken from chemical raw materials called coupling agents or sizing. The manufacturer is a manufacturer of fiberglass, and they use this material, the coupling agents, to stabilize the fiberglass during the manufacture. And we have here three compounds used by this company coming from one supplier. So we'll call these supplier A. And there are three different materials. And you can see, if you look closely, they have a large peak here in common, but the rest of the spectrum is very different. So it's obvious that these three materials are different compounds. You look at the same three compounds from another supplier, supplier B, and again we can see from the spectra that these are clearly different compounds. Now we look at one of the compounds and compare the compound from the two different suppliers. So this is the compound 560. This is the spectrum of 560 from supplier A. And this is the spectrum of compound 560 from supplier B. And we can look at these two spectra and we can see that this is the same material. So clearly supplier A and supplier B are supplying the same compound as 560. We look at compound 570 from supplier A and supplier B. And again, we can see very clearly, just by looking at it, that these two compounds are the same. But now we look at compound 550 from supplier A and supplier B. And in this case, we can see that there are some very significant differences between these two spectra. So this indicates that one of these two suppliers is not supplying the correct material. We don't know which one it is, but clearly supplier A and supplier B are providing something different as compound 550. So this is a very useful quality control test for this user, for this manufacturer, so that they can test their incoming materials. Oh, excuse me, I'm sorry, I'm moving too quickly. So the chemical manufacturer in this case was able to use NMR without any special knowledge, just by looking at the spectrum to see which incoming materials were the right ones and which ones were faulty. So let's move ahead now and look at one of the other important aspects of this instrument, which is the broadband capability. the X-pulse has interchangeable preamplifiers, which we call X-pods, in the front of the magnet unit. And they can be set to monitor any NMR nucleus that you are interested in. And you can change which nucleus you look at by taking the X-pod off the front of the magnet and substituting a different one. And you can have as many of these as you want. They're interchangeable, and you can look at any NMR, any nucleus that gives an NMR signal. This is an illustration of the range of nuclei which are possible. So, for example, if you're in a teaching laboratory, you're probably interested in proton, fluorine, carbon, maybe phosphorus for some organic chemistry. Pharmaceuticals would cover the same range, and maybe lithium as well. Lithium batteries have a wide range of nuclei of interest. Petrochemical, polymers, and food and agriculture also cover a range of different nuclei that could be of interest. And the X-pulse can study all of these different nuclei. Some more examples of the broadband capability. This is similar to one that I showed you earlier. This is a carbon spectrum of the painkiller called ibuprofen. And you can see that the spectrum is very well resolved, very sharp peaks for the carbon atoms in this molecule. And this was done in about 6 minutes, requiring 512 scans. It is very good performance for a small instrument on the benchtop. Here are some other examples of spectra of different elements. In the center here we have a boron and carbon, of course. This is a silicon spectrum. We're starting to see a lot more interest these days from chemical companies looking at silicon-based chemicals. So this is a very useful capability. This is lithium. Not a very interesting spectrum, I'm sure you'll agree. But the position and the shape of the peaks sometimes tells you something useful about the compound, not necessarily just the number of peaks that are there. So this illustrates the wide range of capabilities of the X-pulse. This is an example of a fluorine measurement. Excuse me. Showing you that we can get very high quality spectra of fluorine-based compounds. And we can also do 2D measurements with plotting a fluorine spectrum against a proton spectrum in a fluorinated material like this one here. It's a fluoroether. And this, as with carbon and hydrogen 2D experiments, this plot helps you to identify which fluorine atoms are connected to which hydrogen atoms. It's another example of multi-nuclear capability. This one is used in the batteries industry to look at the electrolytes in lithium batteries. So people making batteries are interested in protons, fluorine, phosphorus sometimes, for phosphorus pentafluoride. and also lithium. So just to summarize that section, the X-Pulse has multiple X-pods or preamplifiers on the front that allow you to cover a wide range of nuclei. You can have single nucleus X-pods, or you can have one that covers 2 nucleus, or you can have one that covers a multi-nuclear, and you can choose the nucleus that you want from software. Let's now talk a little bit about how you use the X-Pulse for doing measurements of flowing samples. The X-Pulse has a specially designed flow cell that fits inside the magnet, and you can pump reaction chemicals from a reaction vessel through the flow cell for measurements online. And the software is arranged so that it takes spectra at regular time intervals, and you can see the starting materials let me run this again. You can see the starting materials, and you can see how the experiment develops. Here you see the starting materials, and as the reaction progresses, the starting materials begin to decrease, and the production at the end of the reaction starts to increase. So you see the change in the reaction mixture as it goes from start to finish. This is a diagram showing in a bit more detail how the system goes together. So here's the magnet. This is a flow cell. We use a pump to circulate fluid or reaction chemicals through this circuit from the reaction vessel and then back in at the end. On the outside of the flow cell is a very thin volume where we put a lock solvent so that you don't have to put a lock material into the reaction vessel. It's contained permanently on the outside of the flow cell. Let me show you some results from a simple flow experiment. So we're starting with a very simple molecule here. Yes, ethyl acetate. This is what the 1D spectrum looks like. It's really quite a simple spectrum. And now we're looking at that same spectrum, but in a flow system. There's no reaction here. This is just a test of the flow capability and the sensitivity. So we're starting by, at the bottom here, flowing this sample through the instrument at a rate of 1 mil per minute, and then increasing in flow rate up to 10 mils per minute. And this simple experiment shows us that we can get meaningful results even at relatively high flow rates of 5, 6, even 7 milliliters per minute. So it illustrates that the flow system works quite well, and we can expect to get reasonably good results even when the sample is flowing. We can even get advanced 2D experiments during a flowing experiment, a flowing measurement. So this is what's called a homonuclear. It's proton versus proton to show couplings between the different protons. And this example was a flow rate of 1 milliliter per minute, running over a total of about 12 minutes. And you can see that this display, this 2D acquisition is really quite good. Almost as good as you would expect from a static sample. But this is flowing at 1 milliliter per minute. This is the same material, this time flowing at 10 milliliters per minute. And you can still see more than enough detail in this display to be able to get useful information about the structure of the material and the way it's changing. This is another example of monitoring a reaction during the flow. So it's a fairly simple reaction. So this is the reaction shown here with the starting materials and the expected production from this reaction, the ending point. So we take a series of measurements at 2-minute intervals, a flow rate of 1 milliliter per minute, and we plot the spectra that we obtain from this reaction mixture every 2 minutes. And you can see in this stacked plot that the starting material is shown here, but that decreases over time. The reaction products are not present, of course, at the beginning, but the peaks from the reaction products appear later in the sequence. And you can plot the integrals as well of the reaction product and the starting material in a graphical form like this. The software that we use for this can be used to do reaction kinetic calculations, such as the Gibbs free energy and using this A-ring Polanyi. I confess that I don't know what that is. I'm not a chemist, but the chemists in our company tell me this is an important thing to use. So you can do these kind of calculations on the data that comes from the flow experiments. This is a range of experiments, also flow, but done using a range of different temperatures from 22 to 72 degrees Celsius. And by observing the reaction rates and calculating parameters from it, you can determine these important characteristics regarding the reaction kinetics. And we'll just talk for a few minutes about some of the more advanced features of the X-Pulse. Those of you who have some experience using high field instruments will hopefully appreciate this. If you don't have experience of high field instruments, it won't mean quite so much to you. But at least you will have an appreciation of what Benchtop NMR is capable of doing. So this is a common requirement in NMR, is to employ a process called solvent suppression. Because normally in any spectrum, there's a very large peak coming from the solvent. Sometimes it's just water, sometimes it's an organic solvent, but usually the solvent peak is the biggest peak in the spectrum. If you don't do anything about the solvent peak, then because this solvent peak is so big, all the other peaks in the spectrum appear as very small bumps on the baseline of the spectrum, because they're overwhelmed by this very large this very large solvent signal. Like any advanced instrument, the X-Pulse is capable of doing what's called solvent suppression. So we can apply very specific radio frequency pulses at this specific frequency where the solvent peak appears, to cause that peak to be suppressed. And when you do that, when you suppress this solvent peak, all the other peaks that were previously hidden on the baseline are now visible. So you can see that in the spectrum here, without solvent suppression, there were a lot of small groups here, but we can't see any detail of what they are. If you suppress the water peak, then those other groups become much more visible. And especially interesting is this glucose peak, which is shown here, which in the unsuppressed spectrum was somewhere down here in the tail of the water peak and completely invisible. But after suppression, that glucose peak is easily visible. Another advanced experiment or measurement that X-Pulse can do is called TOCSY. This is total correlation spectroscopy. It's used to look at the correlations between neighboring protons, and it looks at the connections between any group of protons which are separated from other protons by a quaternary carbon in here that has no protons attached. So we can adjust the experiment so we're looking at only groups of protons which are interacting with each other. And we can see the interactions by looking at the cross peaks here on the opposite sides of this diagonal. So these groups tell us which groups of protons are connected together. This is excuse me, 1 second, need some notes. This is an example of one of the inverse sequences that I showed you much earlier. This is called HSQC, and this is used for identifying protons and the carbons that they are immediately attached to. So this is a proton spectrum. This is the carbon spectrum. And these this display here shows which protons are connected to which carbons. You will notice also that there are different colors on this display. This is like the experiment I showed you earlier. This is a multiplicity edited, that's ME. It means that the CH, the CH2 and the CH3 are shown in different colors to help to identify what the groups of carbon and protons really are. And interesting that we see here, for example, the blue color indicates that this is a CH2 group. And we can see from that that these two proton peaks are connected to the same carbon peak. So this gives us some indication that in fact this carbon peak here is probably coming from two different carbon atoms, even though it appears at the same position in the carbon spectrum. There are two connections. So this helps us to get some information about the near neighbors of each of the protons in the spectrum. This is a technique called selective excitation, which allows us to look at specific parts of a spectrum and ignore the other parts. This example here uses two different compounds. So this is a mixture of these two compounds here, ethyl crotonate and hexanoic acid. This is a simple mixture of the two compounds and shows the peaks in both of them together. Using this selective excitation called TOXI, we can choose to excite only a certain group of the protons in the molecule. So if we choose to irradiate this group here that lies at about 6.5 ppm on the proton scale, we irradiate just this group, and we see only the peaks that come from within that group, broken by this carbon here, where there are no more protons attached. Similarly, on this one here, we can choose to irradiate only the protons coming from this group here at around 3.8 ppm. And we see then only the proton resonances coming from within this group. So we can use this selective excitation to simplify the spectrum by looking just at certain groups at one time and removing the other groups which are making the spectrum complicated. And then finally, on this example, we choose to irradiate here at about 2.8 ppm on the scale. What we see is all of the peaks from the I think this is from the hexanoic acid, yes. So we get all of the peaks here from the hexanoic acid, because all of these protons are connected through the length of the molecule without any breaks. In the case of the ethyl crotonate, this oxygen here causes a break in the spectrum where there are no protons here. So we can irradiate the left side or the right side separately in the examples above. With the hexanoic acid, there is no break in this molecular chain. So with the TOXI, we see all of the peaks in that molecule together. X-pulse has pulse field gradients with it, which means that we can also do diffusion measurements. And these are very often important in the battery industry for looking at how the battery electrolytes diffuse through the mixture. And we can look at temperature dependent diffusion as well, as shown here. So this is just looking at water. It's not any special experiment. It's just to prove the capability of the instrument. Looking at the self-diffusion of water at 18.7 and just over 60 degrees Celsius. Just really showing that the instrument can do diffusion measurements like this. I'm not going to go through and describe all of this, but this is a complete list of all of the experiments, the simple 1D ones here, and the much more advanced 2D experiments in here. These are all the things that the X-pulse can do. And most of these experiments normally were only done on high field instruments. And this shows you that, in fact, there's very little that high field instruments can do that these low field benchtop instruments cannot also do. Now, just before we finish, I have just a few slides to show you about the software. So we have our own acquisition software called SpinFlow. And then we use a commercial software package called MNova, comes from a company called Mestrolab, to do the data processing after the acquisition. So this is what our SpinFlow software looks like for doing the acquisitions. And we have 3 levels of this software. The basic level is a kind of click and go experiment, where we have a list of common experiments shown here in this box, with the parameters already preset for all of those experiments. So all you have to do as a user is choose the experiment you want to do, and then press this go button here. And the measurement will run automatically without any need to set any parameters or do any setting up. And this is very good for people who don't use the instrument very often, not familiar with the parameters, and also for education. So students can be given a set of experiments in here, set by the lecturers and the teachers, and they can't play around with the system and make their own experiments and change the parameters. You can give them a fixed list here that they can work from. The next level is similar, but we allow the user to design their own experiments and set their own parameters. So you can start with our experiments, change the parameters, and save them again with your own name. So you then put them into a list of your own. And in the same way, somebody else can come along and choose one of these measurements from the list and run it without any further need for setting up. So it's a variation of the click and go, but it allows you to design your own experiments to go into the list. And finally, for the NMR experts, there is an advanced level where you have complete access to all of the parameters of the measurement, and you can adjust anything that you want to do, including writing your own pulse sequences if you want to, using our built-in programming language. So I think the software has something for everybody, from basic users to advanced experts. So I'll just leave you now with this final summary slide to show you what high resolution benchtop NMR in a modern form is able to do. So just to recap, it's 60 megahertz high resolution with a 0.35 line shape, has a broadband channel, so we can look at any NMR nucleus. We can do flow measurements, we can do variable temperature measurements, and we can do most of the advanced experiments that normally are only done on high field instruments. So that's the end of the presentation. I hope everybody got something from it, and I hope you've learned something about benchtop NMR spectroscopy. So thank you all very much for joining.
Okay, Mr. Barry Jones, thank you for the presentation. And we have a few questions in here. The first one, Does the instrument require automatic or manual shimming?
Shimming.
Does the shimming? Okay.
Shimming.
Right. There are two levels of shimming. The first shimming is done when the instrument is first installed. So the engineer who does the installation will do the first shimming, which takes about an hour. And it's semi-automatic, but the engineer will take care of all of that for you. You do not need to be involved with that. The second level of shimming is a completely automatic shimming that we recommend for you to do each day at the start of your working day. It takes about 10 minutes, but it's completely automatic. So you never need to do any manual shimming, either during the installation or during the operation.
Okay.
Sorry,
The next
Barry.
one.
Sorry,
Yeah.
there's a second question.
Yeah.
Does Oxford Instrument or this X-Pulse already have the auto sampler?
No, we don't yet. It's in our development plan, but we don't have it yet.
Okay. Please continue, Yulianto.
Okay, thank you, Mr. Agus. The next one, how about the temperature experiment?
Okay. There are two ways of doing a temperature experiment. One way is to use the flow cell and change the temperature of the reaction fluid externally. So you would change it in the reactor. The magnet in the X-Pulse is quite large and heavy, which in some ways is a disadvantage, but it also means that the magnet has very good thermal stability because it has a lot of thermal mass. So changing the temperature of the flowing sample does not have any significant effect on the magnet. And we've shown that we can do flow measurements between about 20 degrees and 70 degrees. So that's one way, is that you have a flowing sample and you change its temperature externally, probably in the reaction vessel. The other way we do temperature measurements is with a variable temperature probe. So that uses a static sample, just a normal 5mm NMR tube, but the probe is a variable temperature probe, and we put controlled temperature gas into the bottom of the probe, just like in a high field instrument. And we can change this, we can run samples in that way between 20 and just over 60 degrees. So you can use either one of those methods to do variable temperature measurements.
Okay, thank you, Mr. Berry. The next question is, can we process the spectra using kind of mass rate Nova or other software?
Yes, you can. You can have an offline version of MNOVA. So you can install it on as many other computers as you want to. There may be a small licensing fee to do that, but you can certainly do that. You can take the data off the instrument and process it externally. And you can generate data files from the instrument that you can process with third-party software as well, if you prefer. So it's very flexible in that respect.
Okay, thank you. The next question is regarding the flow NMR. Do we still need deuterated solvent?
No. Well, Yes, you do, but not in the flow material. Let me just see if I can find another slide that will show you something. Actually, no, it's. I think that's too difficult. Let me come back to this. Let me see if can you see that picture of the flow arrangement?
Yes.
Yeah, okay. It's not very clear from this picture, but the flow tube here is in fact two tubes, one inside the other. The inside tube is where the sample flows, but then there's another tube on the outside of that, which you can't see in this diagram, but the outer tube is sealed, and you can put a deuterated solvent into that external tube. So we can do the lock on the external solvent around the outside of this tube. And it's not necessary to put a deuterated solvent into the reaction mixture. Of course, nobody would want to do that, and it would not be very practical. So this is the way that we solve that problem, by having two concentric tubes. The outside one is completely sealed and holds a deuterated solvent, and the inside one is where the flow, where the sample flows.
Okay, thank you. The next question, are this NMR can be used either in flow synthesis instrument or batch reactor?
Yes, either of those. If it's a batch reactor, you can flow the sample out of the reactor through the NMR and back into the reactor. If it's a flow system, again, you can do the same thing. You can just take the sample out of the reactor and flow it through the NMR and then onto another process, if that's the way it works. Or you can extract manual samples without flowing. All of those possibilities are there.
Okay, the next question is, for the temperature dependence experiment, does the NMR need additional external cooling system?
Yes, we have to supply gas, usually just air, at a controlled temperature. That's the way the variable temperature probe works. So if you want to do variable temperature measurements using the variable temperature probe, then we have to supply some additional equipment to heat or cool and control the temperature of the gas that is blown into the probe from the bottom. That's the way it works.
Okay, thank you. The next question is, how about operational and maintenance costs of the NMR?
The costs are very, very low. Because this is a permanent magnet, as I said in the beginning, there's no need for liquid helium, no liquid nitrogen. There's no spinner in this system, so you don't need compressed air to run it. So really, there are no consumable costs at all. The only cost is for the electricity to operate it, and it uses standard mains electricity. It does need to be put in a stable temperature laboratory, so you would have to have this instrument in an air-conditioned lab with good temperature control. But for the instrument itself, there are basically no consumable costs. You buy it, and well, I suppose the only consumable is the NMR tubes. But most people reuse their NMR tubes until they break them. but that's the only consumable cost.
Oke, thank you Mr. Barry Jones. Bagi bapak-bapak dan ibu-ibu sekalian yang ingin mengajukan pertanyaan bisa diajukan via chat box. Okay, Mr. Barry Jones, can I ask you some question? So,
Yes, of course.
Okay, the tubing for a flow reaction, do you have need a specification for running a flow reaction?
Yes, I don't have it in front of me now, but I can certainly give it to you. It's just standard PTFE tubing used for HPLC measurements, and the connections to the flow cell are standard HPLC connectors. So there's nothing special about the flow tubing at all. Any laboratory probably has this the tubing and the connectors available already.
Oke, siap. Oke, thank you. Jadi untuk bapak-bapak dan ibu-ibu sekalian, jika ada pertanyaan mungkin bisa diajukan via chat box. Oke, sepertinya tidak ada.
One last question, I think. Can I?
Okay. Yes.
Yes, I'm interested with this flow NMR experiments, actually. When you talk about we still have to use kind of deuterated solvent inside the tube, even though it was sealed outside the flow of the reaction. How about the interference from the solvent coming from the reactor? Do we have to manipulate by the software or how?
Well, the solvent that we use for locking, as we said, is in a sealed tube outside the flow tube. There is a small hole in that external tube, so you can actually change the locking solvent that you use. And once it's in there, it doesn't. It's not part of the flow circuit, but you can change the locking solvent if you need to. Your question is about the solvent that's used for the reaction itself. You would have to deal with that either using a solvent suppression technique or adjusting the solvent so that it has peaks not close to the peaks that you want to measure. But that's not something that we can control directly on the instrument. That's a factor involved in your flow experiment. The NMR instrument can't control that directly, of course.
Okay, thank you.
Okay.
Oke, bagi Bapak dan Ibu yang ingin bertanya, bisa diajukan via chat box atau mungkin dinyalakan mic-nya. Baik, mungkin sepertinya cukup. Tidak ada pertanyaan lagi.
Ya, udah clear.
Ya, baik Pak Jamal, terima kasih untuk pertanyaannya. So for Mr. Barry Jones, I think we have done today. Thank you for attending our webinar.
Okay.
Thank you for your time. Dan bagi bapak-bapak sekalian dan ibu-ibu sekalian, terima kasih telah menghadiri webinar kami. Mohon maaf apabila ada kesalahan dalam penyampaian atau kesalahan kata dari kami, mohon maaf. Untuk sertifikat akan kami kirim via email dan via WhatsApp setelah webinar ini selesai. Jadi Bapak dan Ibu sekalian untuk waktunya terima kasih. Selamat sore. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, everybody, for listening and for your excellent questions.
Okay.
Okay,
Yeah.
thank you, Mr. Barry Jones.
Thank you.
Okay. Thank
Bye.
you. Bye-bye. Bye-bye.
Bye.